Welcome to the fourth part of module 4 stereochemistry, that is optical isomerism. So in this presentation we will be discussing about optical isomerism, the reason for optical isomerism, optical isomers and its different examples. Optical isomerism. So we have seen earlier that optical isomers are those which can rotate plane polarized light. We have seen what is plane polarized light. Light which is polarized or which has vibrations in only one plane. Such compounds are called optically active. Optically active compounds. Compounds which rotate the plane polarized light to the right are called dextrorotatory. There are two types of optically active compounds, dextrorotatory and levorotatory. So if the plane polarized light is rotated clockwise, then that is called dextrorotatory. That compound is called dextrorotatory, represented by the symbol small d or a plus sign. And if the compounds rotate the plane polarized light to the left, that is anti-clockwise, then they are called levorotatory, represented by the symbol L, small l or a minus sign. So these are the two types of optically active compounds, dextrorotatory D, and the D and L isomers have same degree of rotation but opposite sign. Now this rotation is measured as a degree, how much degree angle it rotates the plane polarized light. For example, D sucrose, it has a rotation of plus 66.5 degrees, which means that the plane polarized light is rotated by an angle 66.5 degree. Similarly, L sucrose, it is minus 66.5 degrees. That is in the opposite direction, anti-clockwise and clockwise. So the magnitude of the angle is the same, but the sign is different. So plus sign is used when the rotation is to the right, and minus sign is used when the rotation is to the left. The cause of optical activity is asymmetry in the molecule. Asymmetry means lack of symmetry. Okay, lack of symmetry. Now, how does a lack of symmetry come? That we will see. How can we find out whether a molecule is optically active or not? So what you have to do is you have to take the mirror image of this molecule and you have to check whether the mirror image and the original image are superimposable or not. Any molecule which has non-superimposable mirror image will be optically active. Now what do you mean by superimposable? So if you take the mirror image and you place it on the original image, if it fits exactly, that is superimposable. We will see one example later. And if it does not fit exactly, that is non-superimposable. So any molecule which has non-superimposable mirror image will be optically active. Optically active compounds contain at least one asymmetric carbon. Asymmetric carbon means a carbon which is singly bonded to 4 different groups, and that has another name. It is also called as chiral carbon. So if a molecule contains at least one chiral carbon, that molecule will be optically active. So this is another way to find out whether a molecule is optically active or not. Check whether it has a chiral or asymmetric carbon. If there is at least one asymmetric carbon, it will be optically active. Is ethanol optically active or not? That is a question. So how can you find out whether ethanol is active, optically active or not? This is the structural formula of ethanol, CH3CH2OH. Now there are two ways. Either you find out the number of chiral carbons, or you draw the structure and check whether the image is mirror image is superimposable or not. The two ways are there. Now if you look at this molecule, if you look at the central carbon, okay, this carbon, if you look at this carbon, now this carbon is attached to a methyl group, an OH group, and there are two hydrogens. Okay, so this is not a chiral carbon. Okay, this carbon is not chiral, because chiral carbon means it should be attached to 4 different groups. Here this attached to 2 hydrogens, so it is not chiral. So ethanol cannot be optically active. Or another way is you draw the structure. So in this case we can use the Fisher projection formula. Okay, Fisher projection. So if you draw the Fisher projection for ethanol, you will be getting something like this. This is the central carbon. This is these 2 hydrogens, one OH, and this is one CH3. So this is the Fisher projection for ethanol, and check whether its mirror image is superimposable or not. So this is the mirror image. Draw a mirror, and if you look at the mirror image is like this. Now just check whether this mirror image is superimposable. Take this mirror image, just place it on this. You can find that it is exactly fitting. So if it is exactly fitting, it means that it is superimposable, and this molecule is therefore optically inactive. So ethanol is optically inactive. Why? Because it does not have a chiral, that is an asymmetric carbon. Another molecule, let us check, is lactic acid optically active or not? Lactic acid, is it optically active or not? So this is the structure of lactic acid, CH3, CHOH, COOH. Now you can see here this carbon, it is attached to 4 different groups, so it is asymmetric in nature. So lactic acid should be optically active. We can confirm that by checking the Fisher projection. So this is the Fisher projection formula for lactic acid. This is the central carbon, and this is the OH, H, COOH, CH3. So this is the Fisher projection for lactic acid. Now what you do, take a mirror image, and this is the mirror image of lactic acid. Now check whether this mirror image is superimposable. Take this image, place it here. It does not fit exactly, okay, because here you have OH, and here the OH and H is like this, here the OH and H is like this. So if you take this and keep it here, it will not be suiting exactly. So it is non-superimposable, and therefore it is optically active. So lactic acid is optically active. So this is the plus lactic acid, and this is the minus lactic acid. The Fisher projections for plus and minus lactic acids respectively. Optical isomers which are non-superimposable mirror images are called enantiomers. So in the earlier case, we have seen the optical isomers, they are non-superimposable mirror images, and the plus and the minus lactic acids, they are called as enantiomers. That is the technical name. A mixture containing equal amounts of both enantiomers does not show optical activity. So a mixture, if you take a mixture of equal amounts of both the isomers, equal amounts of plus and minus lactic acid, that mixture will not rotate plane polarized light. Why? Because there are 2 isomers, both are miscible, so the rotations get cancelled. One is rotating to the right side, the other is rotating to the left side. Both rotations are equal in magnitude, and so it will get cancelled. So a mixture containing equal amounts of both enantiomers does not show optical activity, because the optical activity gets cancelled. It is called as a racemic mixture. So a mixture of equal amounts of both isomers, both enantiomers, does not show optical activity, and that mixture is called a racemic mixture. It is represented as DL or plus minus. Okay. And the peculiarity of a racemic mixture is that we can separate this mixture into the individual forms. If you take a racemic mixture of lactic acid, then you can separate it into the plus and the minus lactic acids respectively. Now, if you know the number of chiral carbons in a molecule, then we can predict whether it will be optically, or we can predict the number of isomers, not optically active or not. We can predict the number of isomers, optically active isomers for this compound. So suppose there are n chiral carbon atoms, then there will be 2 raised to n isomers. Now in case of lactic acid, we have seen that there is only one chiral carbon atom. So 2 raised to 1, that is there are only 2 optically active isomers, that is the plus and the minus lactic acids respectively. Suppose there are 2 asymmetric carbon atoms in a molecule, for example tartaric acid. Now this is the structure of tartaric acid. So you can see here this carbon is connected to 4 different groups, this carbon is also connected to 4 different groups. So these are 2 asymmetric carbons, and since there are 2 asymmetric carbons, applying the 2 raised to n rule, we can see that 4 optical isomers are possible in case of tartaric acid. Let us draw these 4 isomers. Let us see how we can draw these 4 isomers. We can draw the Fisher projections for these 4 isomers. So this is the Fisher projection for D and L tartaric acids. Okay, this is the D form, that is a plus tartaric acid, and this is the L form. These two are mirror images, and so they are called enantiomers. So 2 forms are like this. Now 2 more forms are remaining, that is known as the mesotartaric acid. So you can see here, this is the mesotartaric acid. So the OH groups are on the same side. That is called the mesotartaric acid. 2 forms are there, meso 1 and meso 2. Now if you compare this meso and the D or L forms, they both are optically active and they are called diastereomers. Optical isomers which are not related as object and mirror images are called diastereomers. So the DL and the meso forms of tartaric acid are diastereomers. This is the structure. So this is meso, the left one, that is mesotartaric acid, and the right one is the D, or you can also draw the L, both are same. DL form of tartaric acid, both are optically active but they are not mirror images, and so they are known as diastereomers. So this is the case of tartaric acid, which contains 2 chiral carbons, and hence there are 4 optical isomers.